This question is about equilibrium. 1 mole of a diester with molecular formula C7H12O4 is added to 1 mole of water in the presence of a small amount of a catalyst. The mixture is left to reach equilibrium at a constant temperature. At equilibrium, X moles of ethanoic acid are present. Complete table 2 by deducing the amounts in terms of X of diester, water and diol present in the equilibrium mixture. So the first thing to do is to look at the ratio. And we can see that we've got 1 of the diester, 2 water, 2 acid, 1 diol. So if the acid goes up by X, and that's in the same ratio as the water must go down by X, that'd be 1 minus X. Now the diol is in a 2-to-1 ratio with the acid, so this would only go up by X over 2. So this one would be X divided by 2. And the diester is in the same ratio as the diol, so this would be X over 2 as well, the change. So this would be 1 minus X over 2. Then it says deduce the structure of the diester. So we're using the information here to help us deduce it. So I'm going to do some working out. Remember, we always cross our working out. We've got 2 ethanoic acids. And we've got this diester, which has 3 CH2s in the middle. So we've got 2 ethanoic acids. Now remember that when you form the ester, so we're breaking up the ester here, but when you form it, then the OH of the carboxylic acid and the H from the alcohol are going to remove as water. So I'm going to cross out this 2 here and write another one of these ethanoic acids at the other side backwards so that I can see what's going on. So again, we're going to get rid of water. So what we're going to do is we're going to join those chunks together. So we've got a CH3 joined to a C with a double bond O, joined to the oxygen of the diol, which has 3 CH2s in the middle, joins to the other ethanoic acid at the other side. A new equilibrium is mixture of the substances from 5.1 is prepared at a different temperature. Table 3 shows the amount of each substance in this new equilibrium mixture. The equilibrium constant is 0.616. Calculate the amount of water in moles in this new equilibrium mixture. Now first thing I would do is I'd write the Kc expression, because it's a Kc value. Remember, it's a fraction. On the top line of the fraction, you have the products, and the powers would be raised to the number of moles of that thing in the balanced equation. And remember, concentration is squared brackets over the reactants Now, we haven't been given the volume in order to find these concentrations, but we don't need it because the volume's the same for everybody, and there are equal number of moles on both sides of the balanced chemical equation, 3 on the left, 3 on the right. So there would be 3 volumes on the top line and 3 volumes on the bottom line. They would all cancel out. So we can just put the moles into this expression in this scenario where there's no units. If there's no units, the moles are cancelled out. So the moles on each side are the same, so the volumes have cancelled out. So I'm going to put the numbers in. So we've got 0.452 times 0.273 divided by 0.971 times the thing we need squared. Okay, so I'm going to rearrange and say x squared. So I'm going to times both sides by x squared. So I'm not changing 452 squared, I'm not changing 273, I'm not moving the 0.971. Then I'm going to divide at the same time both sides by 0.161. So I get x squared equals. I'm going to put all of that into my calculator. And if I do that, I'm going to get 0.357. So I'm going to square root it to get x. And that's going to be 0.597.